In this video, we're going to practice finding the molecular mass of a gas to start. So I have a sample of gas. It's in this container. That container is 255 milliliters. The temperature is 25 degrees Celsius. The pressure is very low, 10 torr. And the weight of the gas inside is 12.1 milligrams. See if you can solve this molecular mass. All right, well, if you're back, there's a couple ways that we can go about this. Think about the different things we know for gas laws. PV equals nRT is kind of our default, ideal gas law. What do I know? I've got a volume, we're good. I've got a temperature, we're good. I've got a pressure, we're good. I could find the moles. I could find out how many moles are in this container. And I have a mass. So if I had mass divided by moles, well, grams over moles is molecular mass. I can use the ideal gas law to solve out our molecular mass by finding the moles of that gas. If I want to do that, rearrange, our moles are going to equal PV over RT, 10 torr, milliliters to liters, 0.255 liters for our volume. I'm in torr, so 62.36 torr liter mole Kelvin. And temperature, well, I need to be in Kelvin, so 25 plus 273 for 298 Kelvin. 0.000137 mole of gas. So we know how many moles are in this container, and we have the mass. Let's convert milligrams to grams. So 0.0121 grams over 0.000137 mole comes out at 88.2 grams per mole. So we can find the molecular mass of this gas, which is extremely helpful in determining what the species is. Very few molecules that can be gases are going to add up to 88. This does assume that all the gas in our container is the same gas. If you can't know that for certain, it's a little hard to guess the molecular mass of it. But if you can be fairly certain that you have only one gas, this is a fine method to find that molecular mass so we can identify the species. But there's another way to do this as well. Think back when we had density of our gas. That's equal to pressure times molecular mass divided by RT. And our density is really mass over volume. Molecular mass is part of this calculation. We don't even have to do a second step. We can find the molecular mass directly if we reorganize this calculation. Our R and T would need to go up, our pressure would need to go down, and we'd be left with molecular mass on its own side. If we try that, 62.36 torr liters mole Kelvin, 298 Kelvin, 0.0121 grams for the mass. Pressure, 10.0 torr. Volume, 0.255 liters. In this case, I've got liters on top and bottom. I've got torr on top and bottom. I've got Kelvin, Kelvin. I'll be left with grams over moles. So this will give us a molecular mass. And we'll find that 88.2 grams per mole. These are just two reworkings of the ideal gas law. One was taking the ideal gas law directly, calculating out moles, and then dividing the mass by the moles. One of them is taking the density equation, rearranging it so that you will end up with mass over moles when you do the calculation. And so it does it all in one step instead of two separate steps. but either route is a fine route to find the molecular mass for a gas from our starting data. Our next problem, we had a sample of gas. It was 3.620 grams of an unknown gas. Well, through various processes, we can break it down and turn it into 2.172 grams of dioxygen and 1.448 grams of sulfur. That gas originally was in a 1,120 milliliter container. The pressure was 75 centimeters of mercury, and it was at 25 degrees Celsius. We're going to take a second and see if we can't figure out the molecular formula. Can we solve the molecular formula for this gas? Go ahead and pause and give that a try. All right, if you're back, well, as we just did in the last problem, we can find molecular mass. Your density is equal to pressure, molecular mass, over RT. Now, why we want molecular mass? Well, we know the elements, sulfur and oxygen. Now, they were probably in different combinations originally, but if we know the molecular mass of that gas, we can figure out what the gas species was. There's only so many combinations of sulfur and oxygen that will add up to any specific weight. So can I solve for this molecular mass? We'll rearrange again. My molecular mass is going to equal the mass RT over the pressure and the volume. 3.620 grams. Our pressure, centimeters of mercury. Well, that's going to take a little conversion. We have a R value for millimeters of mercury. But hey, there's, in every 1 centimeter, 10 millimeters. So really this is just 750 millimeters of mercury. I have to shift to decimal once. So we have our R value. It's going to be 62.36 millimeters of mercury times liters over mole Kelvin. That's also going to change our pressure underneath, but we'll get to that after temp. 25 Celsius is 298 Kelvin. Our pressure, 750 millimeters of mercury. It's not that you can't use centimeters, but by standard we tend to use millimeters of mercury. So if you have to adjust them back into the standard millimeters unit. And our volume, well, it was in milliliters, so divide by 1,000 to get liters, 1.120 liters. Add all that together, comes out just about 80 grams per mole. So our molecular mass is going to be about 80 grams per mole. Well, there's a few options. Sulfurs weigh 32, oxygens weigh 16. I could do 2 sulfurs for 64 and 1 oxygen for an extra 16. That's going to give me 80. So maybe it's S2O. The problem with sulfur and oxygen, their weights are basically, one of them is double the other. So if you got rid of 1 sulfur and said, hey, what if it's 1 sulfur for 32 and 3 oxygen for 48? Well, that will also equal 80. So SO3 could also be a possibility. So there's a couple options here. If we know the differences in our gases and which ones are likely to be gases, we might be able to figure it out that way. But there's another one. We know the actual weights of the chemicals. Assuming that they actually were all the material, because we know the weight we originally put in. So 1.448 grams of sulfur plus 2.172 grams of oxygen. Now it does say dioxygen, but all the atoms there are oxygen, so that weight is just the sum of all the oxygen atoms. Even if it comes in the form of O2, total mass-wise, this is the mass of oxygen atoms. Add those together, and spot on, 3.62. Indeed, all the original mass is part of our sulfur and oxygen. So we know the amount of sulfur and oxygen we really have. We can compare the moles of them. So let's take a second and find the moles of each thing. 2.172 grams of oxygen. So 2.172 grams of O2. Well, there's 32 grams of O2 in 1 mole of O2. And because we want to be in just oxygen to compare, in every 1 mole of O2, there's 2 moles of O. We can find the actual moles of oxygen atoms. 2.172 divided by 32 times 2. 0.136 mole of oxygen. If we do the same thing for sulfur, well, sulfur had 1.448 grams of sulfur at 32 grams of sulfur in 1 mole of sulfur. And, well, I don't need to do the next part. We're already at 1 mole of sulfur. I didn't have to break it apart. In this case, what we'll find is that 1.448 divided by 32, 0.045 mole of sulfur. So I clearly have more oxygen than sulfur. The problem is to figure out how much more. Well, here is where we can exploit mole fraction. Remember that your mole fraction total must equal the mole fraction of A plus the mole fraction of B. If our original gas was the only molecule, if they were the same, if we had had 1 sulfur and 1 oxygen, then each of these would have a mole fraction equal to 1/2. If we'd had sulfur with 2 of them and oxygen with 1, well, out of all the atoms, 2/3 are sulfur and 1/3 are oxygen. And so our mole fraction of sulfur would be 0.67. The mole fraction of oxygen would be 0.33. Our other option was that we had sulfur and 3 oxygens. If this was the case, we'd have 4 total things. 1/4 would be sulfur and 3/4 would be oxygen. So the mole fraction of sulfur would be 0.25, and the mole fraction of oxygen would be 0.75, 3/4. We need to figure out, well, based on our data, what are the mole fractions? We actually have the actual moles that was part of our sample. So which of these formulas does these moles line up with? Well, a mole fraction, the x of anything, is equal to the moles of that gas, or that compound. It doesn't have to be a gas. The moles of that compound divided by total moles. It's just a fraction of the total. If you are 1/2 over 1, then you are 1/2 for your answer. If you are 3 out of 10, you are 0.3. How many out of the total? So for the mole fraction of sulfur, we have 0.045 mole of sulfur. And we need to divide it by total moles. What's total moles? We can add these two together. 0.136 plus 0.045 says that there is 0.181 total moles. So 0.181 total. Sulfur's mole fraction then, 0.045 divided by 0.181. And we will find this is 0.249. Basically 0.25. If we did that for oxygen, 0.136 moles of oxygen over 0.181 total. We'll find that is 0.751, basically 0.75. What we find is that the only one of the formulas, which was really either S2O or SO3, the only one that the number of moles fits with is SO3. And so by knowing the masses of the gas, we were able to find the moles, we were able to compare the moles, and say, well, what mole fractions would we expect for the possible formulas that match our molecular mass? Of the two possible formulas that matched our molecular mass, only one of them also fits our mole fractions. And so the unknown gas we started with was SO3.